Hello and welcome back to the second part of week 7, where, as promised, we are going to be using linear programming as a technique to develop approximation algorithms. And just before we head off into the actual design of algorithms for, say, Vertex Cover, let me just try and recap what the linear programming paradigm looks like. What's a linear program to begin with? Well, a linear program, as you might remember, consists of a bunch of variables, which are sometimes called decision variables because they kind of represent some decisions that you want to make within your problem statement. And these variables are often constrained in certain ways, again, reflecting the constraints that you may have to deal with in your original problem. And typically, subject to those constraints, you want to optimize some kind of an objective function. So just to make that a little bit concrete, let me state some sort of a textbook example so that we have something to play with. So suppose you're a furniture dealer and you deal with two types of items, tables and chairs. And let's say that the costs involved in purchasing a single table would be 2,500 rupees, and for a chair it's going to be 500. So numbers may not be entirely realistic, but they just give us something concrete to work with, so bear with me here. And let's also say that we have a profit estimate of, let's say, 250 from the sale of a single table and 75 from the sale of a single chair. Let's also say that we have some storage constraints, so we can only store 60 pieces of furniture. We don't distinguish between tables and chairs here. We have enough room for 60 units of furniture altogether. And let's also say that we have a budget constraint, so we can invest 50,000 rupees overall. And what we want to do quite naturally is to maximize our profit. We want to figure out how many tables and chairs we should buy so that we maximize our total profit. Now, you could, if you like, take a pause here and just play around with some offhand trial and error estimates of what would happen if you got so many tables and so many chairs. Maybe you only buy tables or you only buy chairs, and you'll find out that basically different combinations lead to different profits. And of course, you have to make sure that your combinations actually respect your storage and your budget constraints. So you have to keep that at the back of your mind. So one way of going about this is to actually write it up as a bunch of equations. And there are two variables at play here. What we don't know is how many tables should we buy and how many chairs should we buy. So let's use two variables to denote these two unknowns. So let's say the number of tables we want to buy is X, the number of chairs we want to buy is Y. And in terms of what we want to optimize for, well, that's going to be the profit. So we want to maximize 250X plus 75Y, because that's the profit that we are going to get when we manage to sell X tables and Y chairs. We're going to assume that we are a really good dealership and we manage to sell everything that we buy. So this is an estimate of our total profit. But of course, X and Y cannot be completely arbitrary, and they're subject to a couple of constraints here. So the first one is the storage constraint, which basically says that X plus Y should be at most 60. And the other one is the budget constraint, which essentially says that 2,500 times X plus 500 times Y should be at most 50,000. So you could simplify that to something like, I think 5X plus Y is at most 100. That's what the budget constraint works out to. And of course, you want a non-negative number of tables and chairs. So that's going to be non-negativity constraints that you can throw in here. And in fact, you probably want to buy a whole number of tables and chairs. So the other constraint that you might want to impose here is integrality constraints, which amount to saying that X and Y are positive integers, right? So that's another constraint that you might want to throw in, so that you get a meaningful output from this program, right? So this is an example of what you might call a linear program. So it consists of an objective function over variables that you're working with, and this is an objective function that you want to optimize. In this case, optimization means maximization, but there could be other scenarios where you're actually interested in minimizing the value of the objective function. That's also fair game. And as you can see, our optimization is subject to constraints, which are again linear functions of the variables involved, and that's where the linear and linear programming comes from. And if you want to further constrain your output to be, for example, only among the positive integers or some subset of integers, then you have what you call an integer linear program to distinguish it from vanilla linear programs where the variables can take real values, basically. So that's the basic setup, and that distinction that I mentioned at the end is actually fairly crucial algorithmically, because it turns out that once you throw in the ability to add integer constraints, then you actually have a very expressive paradigm, and you can in particular encode problems like vertex cover, as we will see. So any algorithm that can solve an integer linear program can in particular solve vertex cover. And so the first reaction that you might have to that is, oh, well, that makes integer linear programming an NP-complete problem. And indeed it does, because it essentially subsumes an NP-complete problem as is a special case. And therefore, for the most part, when we are dealing with approximation algorithms, we only stick to linear programming, which allows for these fractional values. And what we are going to do is basically try and see if we can interpret those fractional values in meaningful ways. The main advantage of sticking to linear programs, as you might have guessed or possibly know from before, is the fact that we actually have polynomial time algorithms that can solve them accurately, and that's what we are going to leverage as we go along. So just to recap, linear programs basically consist of decision variables, linear constraints, and an objective function that you're trying to optimize. And integer linear programs additionally allow you to write down these integrality constraints. So let's go ahead and see if we can formulate vertex cover first as an integer linear program, and then we will throw away the integrality constraints and be left with a program that we can actually solve in polynomial time. And let's see if we can make sense of that solution in the sense of getting some kind of an approximate answer to the original question. So remember that in vertex cover, we are trying to cover edges with vertices. So our input is a simple undirected, unweighted graph. And we want to know if there is a subset of vertices, it's as small as it possibly can be, which is such that every edge has at least one of its endpoints in this subset. So a natural choice for decision variables would be one variable per vertex, because what we are trying to do here is figure out if a vertex belongs or does not belong to the optimal solution that we are after. So if you have a vertex V in your graph G, then let's associate it with a variable that I'm going to denote by X sub V, which takes values in, let's say, 0 and 1. So here I'm imposing an integrality constraint because it gives me this nice semantics, which is to say that if xv takes the value 0, then in my mind that means that I'm not including xv in my solution, or rather I'm not including the vertex v in my solution. And if xv takes the value 1, then I'm going to infer that as saying that I want to include v in my solution. So that's the semantics that I want to associate with this translation. So what do I want to optimize here? Well, remember that we are trying to minimize the size of the vertex cover. So we want to minimize the number of variables that are being set to 1, and that's essentially the sum of the variables xv remember this sum is going to be exactly the number of variables that are set to 1, and this is the thing that we are going to try and minimize. And of course, subject to no constraints at all, we just set everything to 0 and we are happy. That's the smallest possible value that this expression can take. But of course, that's not a very interesting situation to be in. We want our constraints to encode what we want from the set of variables that are set to 1. So what we want from the set of variables set to 1 is that the vertices that they represent should correspond to a vertex cover. So this means that for every edge, we would like that at least one of its endpoints correspond to a variable that's set to 1. So suppose you have an edge u comma v, then corresponding to this edge, you would like to throw in the constraint xu plus xv is at least 1. This captures the idea that no edge is left out by the ILP solution. So I'm going to use ILP to refer to integer linear programs and LP to refer to just linear programs. And so the ILP solution here will ensure that the subset of variables that are triggered to 1 actually form a valid vertex cover. So for instance, let's say you have a graph which looks like this. Then the corresponding constraints are going to be, well, corresponding to the edge AB, you're going to have the constraint XA plus XB is at least 1. Corresponding to the edge BC, you're going to have the constraint XB plus XC is at least 1. And then XA plus XC is at least 1, corresponding to the edge AC. And finally, for the edge CD, you're going to have the constraint XC plus XD is at least 1. So you have these 4 constraints here with 4 variables, and all of those variables take 0, 1 values. And for instance, if you just tried to set XA and XB to 1 and the other 2 to 0, then notice that if you looked at the vertices which are set to 1, so suppose we propose this as a solution to the LP, we say I want to set XA and XB to 1, XC and XD to 0, then notice that if you look at the vertices corresponding to the variables that are set to 1, those vertices don't actually form a vertex cover because you have this edge here that's left out. But notice that you also have a corresponding constraint which is not satisfied by this solution. So this out here is not even a valid ILP solution. And if you stare at this for a couple of minutes, you should be able to convince yourself that the ILP solutions that are valid are in 1-1 correspondence with vertex covers, in the sense that for every ILP solution that satisfies all of the constraints, if you look at the variables that are set to 1, the vertices corresponding to those variables will form a vertex cover back in the graph. And this is the converse is also true. If you have a set of vertices that form a vertex cover, then you can use those vertices to design a ILP solution by saying, for every vertex that belongs to the vertex cover, I'm going to set the corresponding ILP variable to 1. And for every vertex that doesn't belong to the vertex cover, I'm going to set the corresponding ILP variable to 0. And that gives you a solution that's going to satisfy all of these constraints, because that's pretty much by definition. So please satisfy yourself of the 2 statements that were just made if you need, by pausing this video, because that connection between what's going on in the graph structurally and what's going on algebraically in terms of solutions to this ILP problem, that connection is crucial to the correctness of everything that we are going to discuss from here on out. So you can also think of this as a reduction from vertex cover to ILP, because you start with an instance of vertex cover, you come up with an instance of ILP, and the ILP instance has a solution which has a value of at most k for the objective function if and only if the graph that you started with has a vertex cover of size at most k. So if you would like, you can also think of this in terms of a polynomial time reduction, and that's one way to look at it. And notice that and you can also think of this as an optimization question, and since the ILP is trying to minimize the total number of variables that are set to 1, the ILP solutions naturally correspond to the optimal ILP solutions naturally correspond to minimum vertex covers. So hopefully that is clear. But all this tells us so far is that ILP is at least as hard as vertex cover, and we don't have as yet an algorithm that gets us any closer to a solution for vertex cover. So what we are going to do from here is drop the integrality constraints. So we are going to essentially have the same program, but with these integrality constraints actually relaxed so that they allow our variables to take values in the full range of the real interval between 0 and 1. So once we do this, of course, the solutions that we obtain to this relaxed LP don't cleanly correspond to vertex covers as they did before, because, for example, now you might have a solution which says xa equals 0.375 and xb equals 0.7916 and so on. So what do these numbers mean? Sure, they optimize the LP, but what do they tell us about whether the vertex A should be included or not included in our vertex cover? That's not clear because these values are now fractional. Previously, they were binary, so we had a clean signal. If it's 0, don't pick it up. If it's 1, go ahead and include it. But what do we do with these fractional values? Well, one thing that we can do is fairly natural, actually, if you think about it. We try to round these values to their binary counterparts. So we fix a threshold, and for vertex cover, it turns out that a threshold of half is actually fairly natural, and it turns out that this actually works as far as producing two approximate solutions is concerned. So what do I mean by rounding with a threshold of half? What I mean is that we take all the variables that take a value that's at least half and include them in our vertex cover, and all the variables that take values that are strictly less than half are going to correspond to vertices that we don't include in our vertex cover. So let's go back to our earlier example, which was a graph that looked like this, and let's consider a feasible LP solution, which might look something like this. So let's say XC has a value of 0.7, XA has a value of 0.6, XB has a value of 0.5, and XD also has a value of 0.5. Note that this may not be an optimal LP solution. Indeed, I think you can play around with this and make this even better. But for the purposes of our discussion, I just want to work with a feasible solution for now, just to suggest what our approximation algorithm might actually do. So what we are going to do is work with a threshold of half and basically say that every vertex whose associated variable got a value of half or more in the LP solution is going to be included in our vertex cover, right? So for instance, in this example, that would mean that we actually end up picking everything, and that gives us a vertex cover of size 4. Now there are two aspects to this idea that we have to worry about. The first is, well, when we do this, do we always produce a vertex cover? In this example, since we ended up picking everything, sure, we do produce a vertex cover. But on the other hand, is it always true that whenever we work with a threshold of half and basically round up everything that's at least half to 1, is it always going to be a valid vertex cover, or did we just get lucky in this example? So that would be one question. The other is, even if we do end up with a valid vertex cover, what can we say about its size? Does it have any connection with the optimal value? So we are going to answer the first question in the affirmative, which is to say that we will indeed always land up with a vertex cover when we do this kind of thresholding and rounding. And to the second question, the answer is going to be that, well, we will always be within a factor of 2 of the optimal. If you would like, you could pause this discussion here and try to figure this out yourself before coming back, where we will go over both of these questions one by one. Alright, so first let me try to convince you that whatever we pick up will actually be a valid vertex cover. So just so that we are on the same page, our approximation algorithm is the following. We are going to use S to denote our solution. To begin with, it's empty. And then for each vertex in the vertex set, we're going to say if xv has a value that's at least half, then include the vertex v in the solution, right? So that's our threshold and round approach, right? Now, I claim that S is a vertex cover. And let's think about this for a moment. So as we have done before with the matching based algorithm, let's argue this by contradiction. So suppose S is not a vertex cover, and suppose the edge UV is not covered by S, right? That would mean that XU had a value that was strictly less than half, and XV also had a value that was strictly less than half, because that's the only reason that we didn't pick up either of these vertices in our solution. But remember that UV is an edge, which means that our LP must have had a constraint that looked like this. XU plus XV is at least 1. And now if you have both XU and XV taking values that are strictly less than half, then you end up violating this constraint, and that would be a contradiction, right? So as long as we are picking up all the vertices corresponding to variables whose values are at least half, we are good. We will have a vertex cover. Now we turn to the second question, which is what kind of a vertex cover is this? Is this going to be something silly? Like for instance, here we ended up picking everything. Do we always do something extreme like that, or do we actually have a vertex cover that is relatable to the optimal one in some sense? So as I promised earlier, we are going to actually argue that the vertex cover that is output by this algorithm is at most twice the size of an optimal vertex cover. So let's see why that's true. As before, it's useful to have a lower bound on opt in terms of something that your algorithm is doing. In this case, we are working with a LP solution. So let me use LP opt to denote the value of the optimal solution of the relaxed linear program, where the variables are allowed to take values in the full range between 0 and 1, 0, 1 included. So that's LP opt, and I want to claim that the size of a minimum vertex cover, which I want to denote as min VC, is at least LP opt. So in other words, LP opt is a lower bound on the true opt, which is what we are after. So if LP opt is somewhere here, then the value of the minimum vertex cover lies in this range. And well, why is that? Because notice that the minimum vertex cover value is exactly equal to the ILP opt, because the ILP exactly mimicked the vertex cover problem. So the ILP opt is exactly the minimum vertex cover value, and this is something that we have reasoned about before. Now notice that whatever you can do in the ILP, you can do in the LP, because integers 0 and 1 are still included in the valid range of variables in the LP. But on the other hand, the LP has more flexibility in terms of where it can take values, where its variables can take values, and therefore it has a wider array of options to choose from. So perhaps it does a better job of minimizing the objective function. So if anything, by going to a larger space for the variables to take values in, if anything, your opt may drop. It will, of course, certainly not increase, right? So therefore the LP opt is either the same as or is smaller than the ILP opt, but that's exactly the value of the minimum vertex cover, right? So that gives us the lower bound that will be useful to anchor our argument going forward. Now, what do we want to show? Well, I want to show that the output of the algorithm, okay, so that's the size of S, is at most twice the value of the minimum vertex cover. So I'm going to use min VC to denote the size of an optimal vertex cover. That's what I meant earlier as well. And notice that it's enough to show that the size of S is at most twice LP opt, because then we can plug in the inequality that we had earlier to say that this is at most twice min VC. Yes, so we're going to focus on just showing this inequality here, and this is what I meant earlier as well when I said that having this sort of a lower bound is useful because it helps you argue in terms of the bound. And in this case, if you think about it, what are we really doing? We are doubling at best a certain section of values from the variables that contribute to the LP opt, but the only variables that we are rounding are variables whose values are already at least half. So in some sense these values at most double, and that's why this inequality here is true. Just to make that a little more explicit, let's say we're working with an example where we have 5 vertices, and let me again take a random LP solution here. So let's say these vertices have values, right? So let's say that this is, well, I haven't even given you the constraints, it doesn't matter. Let's just say that this is a valid a feasible LP solution, and in particular let's even say it's LP opt. This is what LP opt looks like for some instance of a vertex cover LP. And notice that what's going to happen when we run the approximation algorithm is that these 2 vertices are going to get dropped. We are not going to pick them, and we are going to pick these ones out here, and that basically means that we are rounding up these values to 1. But these were all, by the definition of our threshold, these were all values that were themselves at least half to begin with. So when you round them up to 1, you at most double their value. In fact, we're doing a little less than doubling for values like 0.7 and 0.8. When you replace 0.7 with 1 or 0.8 with 1, you're not even doubling them, you're doing a little bit less. And with 0.5, of course, you're exactly doubling. So remember that LP opt is the sum of, these values that are written in blue here, and the output that we have, which is the size of S, that is the sum of these rounded up values. Okay, so we have dropped a few that are less than half, and we have rounded up a few which are at least half, and therefore the size of S is going to be at most twice the size of LP opt, or the value of LP opt. Yes, and that gives us this inequality here, and from here, like we said, we can derive or conclude that we indeed have a 2 approximation because the LP opt is a valid lower bound for the true optimal, right? So there are 2 key arguments at play here. One is the fact that the LP opt is a lower bound for the value that we are after, and the second is to connect the value of the output with the value of LP opt, and in this case this works out because of the style in which we are thresholding. So in one of the assignment problems this week, you will be able to think about this a little bit more by seeing how the approximation ratio is affected if you change the value of the threshold. So why half? I mean, it sounds arbitrary, so why not threshold at 3/4 or 1/3, right? In one of these cases, the threshold is too weak to even produce a vertex cover. And in the other case, while it will produce a vertex cover, it'll give you an approximation ratio that's worse off. So if you think about this a little bit more, you will hopefully come to the conclusion that half is just the right thing to do in this case, and there isn't a better thresholding value. Okay. So to encourage a little more practice with this technique, I'm going to leave you with one more problem, which is of a rather similar flavor to vertex cover. In fact, you can see vertex cover as a special case of this other problem, which I'm going to call set cover. And in fact, you might remember set cover from some of our earlier discussions as well, when we were doing dynamic programming and so on. But if you don't, then we're just going to describe it here again. So we have here as input a universe U, so that consists of elements E1, E2, and so on, up to say En. And we also have a family F, and that consists of sets S1 through Sm, and each Si is a subset of the universe U, and you can assume that each Si is associated with a weight Wi. Okay. Our goal is to find a smallest weight collection of sets that covers the entire universe. What do I mean by this? Well, I'm looking for a subset of, let's say, 1 through M, such that if I were to take the union of the sets that belong to the chosen subset, then I get back the universe. So every element in the universe belongs to at least one of the chosen sets. And I want this collection to be such that, well, I minimize the weight of the sets that are chosen. So the total weight of the chosen sets should be as small as possible. So this is the minimum weight set cover problem. And as before, you can try to solve this using dynamic programming, but here I want to actually come up with an approach to approximating the optimal solution here using, for example, a LP formulation. So what would be a LP associated with set cover? Remember that the choices that you're making actually are with respect to the sets. You might want to introduce M variables, say x1 through xm, and again these are variables in 0, 1. So if xi is set to 1, that would imply that you're choosing this set in your solution, and if it's set to 0, then you aren't. And of course that's the ILP formulation here. You would have to add constraints to make sure that what you have is actually a set cover. So you will have a constraint for every element in the universe, which reflects the idea that, you know, there is some chosen set that covers that element. So I will leave the formulation of that constraint as an exercise for you. And then think about how would you do the rounding and how would you ensure that you actually have a set cover and one that is somehow close to the optimal one. So think about that, and when we meet next, we will see a different approach to solving the set cover problem, in fact using a greedy paradigm. And then the last thing that we will look at this week is the primal dual approach to finding approximation algorithms. So we will circle back to LP. Given a LP, we will learn how to write the dual LP, and we'll see how to work with the dual variables to actually come up with an approximation for the original problem. So that's what's up next.